So Pierre Mérel is professor of agriculture and resource economics at the University of California, Davis. And he is currently on a research stay in France since January 2021 at the Institut d'études avancées de Paris within the chaire d'Alembert in partnership with the University of Paris-Saclay. Pierre Mérel research focus mainly on climate change and agriculture and food policy. He conducted research on industrial organization, agricultural sector food, nitrogen pollution from agriculture, and agri-environmental policy modeling. So we are very happy to have him today to present his work on double cropping as an adaptation to climate change in the case of the United States. So as Louis said, the floor is yours for 30 minutes, Pierre. Thank you.
Thank you. Thank you for the introduction. I just wanted to say it's actually not the chaire d'Alembert that I got. I got a regular position in the end. They gave the chair to someone else. So I don't want to claim something I don't have. They told me I had it and then they gave it to another person. So apart from that, everything's correct. So this is work that I've been working on with Ariel and mostly one of my students, Matt, who's now at Michigan State for quite a long time. We've submitted the paper several times. There's been a lot of changes in terms of the econometrics, but not so much in terms of the results or the global message of that paper. Which maybe is good news. So we're going to talk about double cropping in the US and how it might or might not turn out to be a panacea to mitigate the predicted effects of climate change on yields. So agriculture will be particularly affected by climate change because weather is an important input into agricultural production. So, this is well known. Even non-ag economists agree about that statement. And so, in a sense, agriculture has been an object of study in the climate change literature by economists, which usually they're not too much interested in agriculture, but when it comes to climate change, suddenly there is a renewed interest. So what are the lessons so far from this research? I mean, it's mostly empirical, and at least for the US, and I could say also other temperate regions, there is both econometric evidence, but also agronomic evidence, which is, older or started earlier than the econometric work on crop yields. The overwhelming evidence is that warmer temperatures are going to decrease yields for many crops and many regions. And today we're interested in soy. And so for the US, the econometric reference of study is by Schlenker and Roberts. It's a highly cited paper that most people look at it because it's about corn, but there's also soy and cotton in there. And for soy, Schlenker and Roberts predict yield losses between 30 and 75% by the end of the century. So the number is big. There's also a big range here. It depends on the climate scenario. So that drives most of the discrepancy between the 30 and the 75%. Of course, there could be reduction in yields, but what we should care about in terms of welfare is not so much yield, but supply. And yield is not exactly the same as supply. First of all, there could be acreage responses, both at the extensive and the intensive margin. So for example, Xiaomeng, who I saw, is going to talk about changes in growing season, also has a paper that he crafted while at Davis on how the relative acreage of crops in the US has responded to climate in the past. So there is an acreage response. And I think he looks mostly at, acreage allocation, so intensive margin changes. And then another margin of response, which is the focus of the paper today, is cropping intensity. That means on the same acre of land, cropping not one, but maybe 2 or 3 crops within a calendar year. So double cropping is prominent in many temperate and tropical regions, in Brazil, Japan, Southeast Asia. In the US, it's very limited. The focus of today's talk is about the winter wheat soybeans double cropping system, which represents 80% of all double cropping in the US. But only 6% of soy is double cropped with wheat. So you can see that the numbers are quite small at present. Soy is an important crop, however, it's the second largest US crop by value. And there is previous agronomic work on this. I think the study of reference is by Seifert and Lobel. And the lesson from that study is that a lack of heat, I mean, there's many lessons, but one of them is that the lack of heat accumulation before the fall freeze is an important constraint to double cropping soybeans with wheat. And so to the extent that warming happens, it may relax this constraint and therefore make a double cropping more prevalent. So what are we talking about when we talk about the winter wheat and soy cropping system? So winter wheat is planted in November, December. It's sown in June, and then immediately afterwards, soy is planted. You can't waste too much time because otherwise there won't be enough degree days accumulated before you have to harvest your soy, and you have to harvest it before the fall frost. So I'm not saying that this climatic environment is the only constraint. There are other constraints, notably in terms of soils. Some soils are not just adapted to grow wheat in the winter, but climate is a big constraint. And so as climate change lengthens the growing season and makes it warmer, so we are expecting the fall frost to be pushed further, and also more degree days to accumulate during the growing season, we could expect DC prevalence to increase. So the study of reference, which I mentioned already, does find that there's a very large increase in the suitability for this double cropping system under warming scenarios, and I think an increase in more than 200% in the suitability in the area that is deemed suitable. However, agronomic suitability or agronomic feasibility is not the same as adoption. And even the Seifert and Lobel paper recognizes it. So you see here two panels that are directly taken from that paper. The one on the left shows the suitability, which is ranked from high to low. I think it's a probability of survival. So that's why we have this scale. And then we have the share of double cropping on from the county records, so what people actually do on the right-hand panel. So you see that there's a big gap between what people could do based on agronomic modeling and what people are actually doing. So that raises the question about whether this suitability index is actually a good way to measure how double cropping might expand, because if you can't even account for what's happening under the current climate, how are we to believe the predictions from these models under counterfactual or future climates? So why does agronomic suitability has limitations? Well, farmers select to single or double crop soybeans in order to maximize profits, or at least that's how economists think that farmers are reasoning. If the climatic constraint is binding, then farmers have no choice. So if the area is not suitable, if the crop has a high chance of failure, then there will be single cropping. But if the climatic constraint is not binding, that doesn't mean that automatically farmers are going to engage in double cropping. And additional factors then enter their decision. And these could be soils. So it could be that the soils are not suitable for winter wheat during the winter, or the yields that you obtain, even if you can plant the wheat, are just not worth the variable costs. Of course, even if there are in absolute, then there could be more desirable options so that farmers don't double crop. Crop prices are going to matter as well. It could be that in 1 year it doesn't make sense, but if you're expecting high wheat prices, suddenly it makes sense to double crop. Opportunity costs matter, of course. So labor, machinery, fertilizers. So the price of fertilizer is not so important maybe for soybeans, but for wheat it is. And so if fertilizer is very expensive, maybe it's not worth growing the wheat. And then even if all the economic conditions seem to be lined up, it could be that there is no local marketing opportunities for wheat because wheat is not grown in sufficient quantity at a given locale. And so you can't really market it unless you incur additional transport costs, and that may make it not profitable. So all of these factors are definitely not taken into an agronomic suitability study, and they do matter, as the two maps that I just showed you indicate. So in this paper, it's an observational study. So that's the main difference. Instead of trying to figure out what farmers should do or could do under different climates, we're gonna look at what they do in actuality, what they actually do, what they actually plant. So we're gonna look at the DC propensity and try to relate it to various factors, including climate, and then projecting into future climate, trying to see how this propensity is going to change. So we are not modeling the choice to double crop per se. We don't have a structural model of adoption. It's a reduced form model where we are basically regressing the propensity to double crop on explanatory variables. But because it's observational, it implicitly includes the economic factors I just listed. So our study is going to be at the PRISM grid cell level. PRISM is a weather database. It's a 16 square kilometer grid. So we're going to have lots of observations. So that's going to be in a cross section. And then we're going to estimate yield effects on soybean yields. So the effect of double cropping on soybean yield. There's some agronomic literature on that, but no empirical studies that use actual yield. So we're going to do that, and we're going to find a yield penalty of 12.1%. So that's the penalty you get if you choose to add the wheat during the winter. This 12.1% is just for the soybean yield. It doesn't count the yield from the wheat, but you get a lower yield of soybeans because you're squeezing the growing season for the soybeans. And also you might have competition for nutrients or water in the soil. And then once we've done this DC propensity estimation and the yield penalty, we're gonna use these two estimates to compute the adaptive benefit of double cropping on calorie production under various warming scenarios. So I don't know how many natural scientists there are in the room, but that's maybe the weak point of the studies. We don't do anything sophisticated in terms of the warmings. We have uniform warming scenarios. So we're not using climate models here. And so the broad message is that yes, DC will increase, but not enough to offset a lot of the yield declines that are predicted by climate change, or at least by the econometric studies. So a little bit of, I wouldn't call it theory, but a methodological framework to try to better identify exactly what we're going to estimate. So here, I is a location. You can think of a grid cell, for example, one of these grid cells I was mentioning. CI is total calories from soybean systems in that grid cell, and it's going to be the sum of the calories from single crop soy and that from the double crop soy. And so in the single crop soy, if I call AI the area in soybeans and SI the share of soy that is double crop, then the area that is single cropped is AI times 1 minus SI. If I multiply that by the yield of soy expressed in calories, I get the calories from the single crop soy. And then I'm going to do kind of the same for the double cropped. soy, except that here I need to take account first of the additional yield of wheat. So that's what I called YIDC wheat, is the additional harvest you get for the winter crop. And then I also account for the fact that if you double crop the soy, you get less yield of soy. So theta here is what we're going to refer to as the yield penalty. It's the percentage decrease in yield if you choose to double crop with wheat. And all these yields are expressed in calorie units. And so what we're interested in is ultimately what we call the adaptive benefit. And to understand what that is, we can take the total derivative of this calorie provision with respect to climate, which I call mu I. I said total derivative, but it's not completely total because I'm holding two things constant here. I'm going to hold the area constant, so I'm not letting the area in soy systems change. So I'm not introducing more corn or other crops. It's just soy or double cropped soy. So AI is constant. So that's not changing with climate. I mean, it is in reality, but I'm ignoring it in my calculation. And the other thing that I'm holding constant is the yield penalty. So this 12.1% that we're going to estimate is also, it's a number. It doesn't change with climate. Well, that's what we're assuming. Then everything else is allowed to change. So the yield of soy changes with climate. That's the Schlenker and Roberts study. The yield of wheat is going to change with climate. That's the Tack et al. Study, although it's for Kansas only. And then Matt and I and Ariel also have a paper on wheat, but it's in France. So we don't have that good of an estimate for the wheat, but we know that the estimate is negative, perhaps not as negative as the soy one, but wheat yields are not predicted to increase under these econometric studies. And then what we're interested in is to compare these yield induced decreases in calories with the effect channeled through changes in the double cropping area. So that's where you see the partial of SI, which is the share double cropped with respect to the climate. We're interested in estimating this. How will the double cropping propensity or the share change with climate? And then to get the effect in calories, we also need this theta here, which is again the yield penalty. So this last term in the equation is what we call the adaptive benefit. And we're going to compare it not so much to the wheat yield effect because we don't have that good of an estimate, but to the effect on yield from the Schlenker and Roberts study. So we're going to estimate, we need two ingredients to compute this adaptive benefit. First, the partial of the propensity with respect to climate. That's going to be estimated using cross-section. And then the yield penalty, we're going to estimate it using panel at the county level, US county level. So first, the cross-section, that's kind of the main part of the paper. So we're going to use the cropland data layer to identify double cropping practices. We're then going to aggregate that at the level of the PRISM data, which is slightly bigger because that's what the weather data is coming from, and therefore the climate data. So if I focus on one county in Washington County in Illinois, that's what I get. So these yellow and green and other colors are fields. The blue grid is the PRISM grid. That's going to be my cross-sectional unit of analysis. And within a grid, you see that I have several fields. So for example, the soy is in dark green and green. And if I change the color to make it a little bit, to make it pop out, I have the green is the single cropped soy and the double cropped soy is in blue. So we're going to compute the double cropping share using all the information we have, or we had at the time we started the paper, which is until 2018. So we're averaging areas in any grid cell G over all these years. computing the areas in square kilometers, and then constructing the share from that. So for that particular grid cell over these years, you see you have 30% of soybeans that is double crop. That's a lot, right? Remember, I think it was 6 or 8% at the national level of soybeans that are double cropped. So here it's a high double cropping propensity. So once we do that, we can compute the current DC prevalence. So here I'm zooming out. So my grid cells are actually looking like little dots. Each little dot on this map is a 4 kilometer by 4 kilometer prism grid cell. And so in dark gray, there is no soybeans at all. In light gray, there are soybeans, but no double cropped soybeans. So everything that's in light gray is single cropped soybeans. And then the hues from green to dark blue are different shares of double cropping with more, bluer or darker shade indicating more double cropping. So you see you have pockets of double cropping in certain areas. So, it looks like climate may be important, but it's not everything. It seems like maybe soils could be playing a role here. Just looking at the geographical clustering. So as I said, the reason why we focus on these 4 kilometer by 4 kilometer grid cells is because that's what that's the resolution of the weather data. And so in our sample, we have 130,000 grid cells. So that's our sample size for the cross-sectional analysis. And we're going to compute climate by averaging over many, many years from 1981 to 2005. The regressors of choice are going to be growing degree days for the whole calendar year, with a 5 degree lower threshold and no upper threshold, and cumulative precipitation also across the calendar year. We use soils data, so we're controlling for soils as well, and with fixed effects. So the fixed effects are constructed around kind of a two-way. It depends on the percentage sand and percentage clay, with the remainder being silt, right? So we have, I think, 15 possible combinations of percentages of clay and sand. And in the sample, I think we only observe 12 of these categories. So we're going to have 12 fixed effects for soils. So each square here is going to have its own fixed effect in the cross-sectional regression. And so the empirical approach we use is basically dictated by the fact that our dependent variable is a share between 0 and 1. And we also have a lot of zeros. There's a lot of dots on this map that were in light gray, sorry. That means these don't have any double cropping, but they have soy. And as they warm up, it could be that they become suitable for double cropping. So we don't want to remove these observations from the estimation. We want to include them. And the way to do that is to estimate one way to do that is to estimate a fractional logistic method. So the model primitive is the expectation of the DC share in a grid cell, which we call SG, conditional on the observables, that is the climate and the soils, and also we include state fixed effects. And so we call these in XG, it's a vector of covariates, and the function G is the logistic cumulative distribution function here, right? And then the XG beta is going to be, again, a function of the GDD and the precip, the state fixed effects, and the soil type fixed effects. And the estimation goes as follows. It's a quasi maximum likelihood estimation based on the following likelihood function that is maximized over beta, the vector of coefficients. And we cluster standard errors at the state level. So this is one of the main graphs of the paper, and it shows you I forgot to say how we enter the GD and the precip. So we have two main specifications, a step function and then a polynomial. And then basically they're going to overlap as usual. So here I show both on the top panel of this graph, but let's start from the bottom panel first. We have the distribution of climates. Here it's growing degree days. I don't think I'm going to show you the precipitation because it's less interesting. So this is the climate distribution from about 2,500 growing degree days to 5,500. Then in the middle panel, you have two graphs that look like they're almost identical. One of them is in solid purple. It's the predicted double cropping share from the model. And then the blue is the actual share. The dashed blue is the actual share observed. And these are average shares across grid cells that fall into each of these GDD bins, right? And then we have the quadratic relationship at the top sorry, it's actually a polynomial of degree 3. It looks quadratic, but it's a polynomial of degree 3, and it's overlaid with the step function, and they kind of match, and we show the standard errors for the step function. So what you see is that more GDD is not always improving the propensity to double crop. It is over a large range of GDD values, but there's kind of a peak apparently around 4,500 growing degree days or so, above which more degree days is going to be damaging. So, and there are grid cells above that peak. So we're expecting that at least in some areas, propensity is going to decline. And if you look at the middle panel, you know, for those areas that are above 40, let's say above 4,500 degree days, you do have double cropping here. There's a high double cropping share, right? So we would expect double cropping in these areas to decrease. So what is the net effect? Well, I'm going to show you that in a couple slides. This one looks almost like the previous one, except for the top panel. So the previous panel showed you the estimation of the what I call the H function. And this is the marginal effect on the DC share. It's a nonlinear model, and it's easy to compute the marginal effect on the DC share from the beta coefficients. And when we do that, we get this nice blue graph that shows that at first, as GDD goes up, there will be a positive effect on the propensity to double crop, which crosses the zero axis a little bit, so still above 4,500, and then it's negative, right? So that's the marginal effect. Well, I'm actually not going to use that marginal effect in the counterfactual. Since we estimate the entire relationship, we don't need to use derivatives. We're just going to evaluate the estimated function at different values of GDD. And so that's what we do here for each grid cell for a 3-degree warming scenario. So again, it's a uniform warming. It changes the average temperature by 3 degrees uniformly, but that doesn't mean that the changes in GDD are uniform, because the GDD are nonlinear function of temperature exposure. So, but even so, that's a very simplistic type of warming scenario, albeit one that is also explored in the Schlenker and Roberts paper, which is nice because then we can compare apples to apples. So in red, you have declines in DC propensity. In blue, you have increases in DC propensity. So you see it's a mixed bag with more red in the southern part and more blue in the higher part of the region under study here. And here it's not in percentage terms, it's in square kilometer. So it's a change in the area. Remember, each dot is 16 square kilometers. So here the scale goes from about minus 3.5 or minus 4 to plus 4. So we have our first ingredient, the orange partial derivative here. We still need the yield penalty. And I'm going to be really quick. So we estimate that at the county level, because that's where the yield data is at, right? We don't have yield data at the grid cell level. We have it at the county level. So we're going to aggregate everything at the county level. It's a panel, but it's a short panel. So for those of you who are familiar with the Schlenker-Roberts paper, I think it starts from the 1950s. Here we start from 2008. Why? Because we don't have the DC prevalence before 2008, because we use the cropland data layer to figure out how much DC there is. So this CDL, which is very, very high resolution, is aggregated to the county year level. And we include weather controls, just like the Schlenker and Roberts. So here it's a little bit different than what we have in the cross-section. We use 3-degree temperature bins like Schlenker and Roberts and a quadratic in precipitation. So basically it's a Schlenker and Roberts regression with county fixed effects, state by year fixed effects, the weather effects specified just as in Schlenker and Roberts. We just add the share double cropped, SCT. And the coefficient in front of this is going to be our estimate of, or minus our estimate of the penalty. Meaning if you go from S equals 0, everything is single cropped, to S equals 1, everything is double cropped, you should expect a decrease. So we expect theta to be positive, and so the coefficient to be negative, the minus theta. I'm not going to discuss bias here, but I'm happy to answer questions about this. And so what we find is a 12.1% yield penalty that is relatively precisely estimated. The estimates on the step function, are not as sharp, obviously, as those in Schlenker and Roberts, because they have a much longer time panel in the time dimension, but they are pretty consistent. So that's reassuring. And what's also reassuring is that this 12.1% seems to be in line with previous agronomic evidence. So now we're putting the pieces together to compute this adaptive benefit. So the equation you see here is kind of the incremental analog to the partial derivative I showed you earlier. So as I said, we're not actually using marginal analysis here because we're estimating the response function. So we have S1 minus S0, that's the change in the share. And then we have our estimate of theta here. And if you wonder why it's at the denominator, it's because the yield that we observe is actually a yield average. So the county yield is a yield average. And so to the extent that there is double cropping in there, it's already capturing some of the penalty. So to get the single cropped yield, we need to divide what we observe by 1 minus the share times the penalty. And then, so because we have two equations with two sets of covariance matrices, we're going to address uncertainty by sampling. So we have 10,000, we generate 10,000 sets of coefficients, and we compute the adaptive benefits each time, and then we construct the distribution of outcomes from that. Bootstrap, that's the word I was looking for. So that's the final graph. So here I show you 2 degree, 3 degree, 4 degree, but you can focus on the yellow, which is the 3 degree scenario I've been focusing on so far. And so there's the distribution of effect. So it's mostly positive, right? This adapted value, and here it's expressed in percent. And most of the mass of this distribution lies between 2 and 3.3%, right? So that's the predicted increase in calorie provision due to the increase in the propensity to double crop soybeans, accounting fully for both the additional yield from the wheat and the penalty from the lower soybean yield. So in conclusion, warm temperatures increase cropping intensity, yes, but up to a point. So there are some areas that don't benefit from warming. That was already something that was actually uncovered in the Seifert and Lobel study, but it's good that we confirm that using observational data. Schlenker and Roberts estimate soybean yield losses of minus 17% under the uniform 3 degree warming scenario. And our study projects an increase in DC area by 53% in total. I don't think I mentioned that number, but it's the net of all the blue and the red that you saw on that map earlier. Using observational data implies much lower uptake of DC than agronomic model. I've said that. Adaptation has cost in terms of reduced soy yields. And once we put all the pieces together, double cropping offsets only a small portion. So we can, the central estimate is about 2.5% of the predicted negative yield effects of warming on US soybean agriculture. So to compare apples to apples, you have to compare the minus 17% from Schlenker and Roberts to the plus 2.5% from the effect of increased double cropping. And then you still have a negative effect from the wheat yield that we have, that we don't have a good estimate for, but we were pretty sure it's negative. So the lesson is that double cropping is going to help, but only, some. It's not a panacea. And I think I filled my time and perhaps even more. I apologize.
Thank you. Thank you very much, Pierre, for this very nice presentation. I don't know if there are any questions. I have one question in the discussion from Ping. So the question is there any other cropping patterns in addition to soy wheat double cropping in your study area?
Yes, there are. So I can share my screen maybe to show you that.
So do you control for that? How do you can?
No, I don't control. I don't control.
Okay.
We're only looking at one type of double cropping here.
Okay.
Let me see. May revision appendix. Yeah, I'm gonna stop sharing what I'm sharing and begin sharing my appendix because the answer is there and I don't know the answer by heart. Yeah, so here in this table, it's the most prevalent double combination. So you have 79% is winter wheat soybeans. The next one is only 6%, and it's winter wheat corn, then winter wheat sorghum, winter wheat cotton, oats, corn, barley, soybeans, and then all other combinations, 2%. And here you have the area involved.
Okay, I don't know if there are any other questions. Yeah, François, you would like to ask your question directly or?
Yeah, I can. Thank you, Pierre. Just one question. I didn't get it from your conclusion. So you say basically that adaptation reduces the negative impact of climate change by 2 to 3%?
No, I didn't speak well enough. So Schlenker and Roberts predict a decrease in yield of 17% under 3-degree warming, uniform. We predict an offsetting 2.5% increase. So in net, you can take 2.5 out of 17 and you have the net effect.
So it's 17.
Two effects, 17 minus 2.5, yeah. So that would be 14.5 in net. And that still doesn't account for the fact that the wheat harvest is gonna probably be less good under a warmer climate than it is right now.
Okay.
Do you have any other questions? David Makowski, you would like to answer your question directly?
Yes, I was wondering, I didn't understand exactly what is the assumption about the wheat monocrops.
Nothing. Yeah. They're not in the picture. So we're only interested in soybean systems. So if wheat is, for example, in Kansas, you have a lot of single cropped wheat. That's not part of our calorie supply. The only calories that are part of our system of investigation are those that come from soybean systems, either soy by itself or soy with wheat in the winter.
Yeah, okay. Because if you are able to grow more wheat in soybean wheat double cropping, you can imagine that we need less wheat monocrops in the agricultural area, and maybe the wheat monocrops will be replaced by soybean monocrops, if more profitable, for example, or if the demand is higher. And in that case, you can imagine that the calorie supply will be changed because, of course, the calorie supply of soybean and the calorie supply of wheat is not the same. So,
yeah, I mean, that's possible. Although, I mean, nothing prevents current. And so you're talking about effects that are channeled through prices, not through climate, but under current. So if it is the case indeed that under current climate, you know, Kansas could grow a lot of soybeans. Yeah, maybe. I mean, nothing prevents them from doing that. Our model is not well suited to study market-mediated effects to crop prices, because these crop prices are determined on world markets. So for that, you need a trade model like Costino et al. Paper in the JPE. This is not, our model is not at all suited to.
Yes, I agree. But even if you think about the pure climate effect, basically, if the temperature increase, the climate will be more suitable for soybean, whatever soybean in double crop or in monocrop. So you could imagine substitution of wheat by soybean.
Yeah, no, I agree, and we're not count. So that's the caveat that I mentioned at the beginning. The AI, the area, is held constant.
Yeah, okay.
We're not looking at expansion of soybeans replaces other crops, which could happen. I totally agree. It could also be that the winter wheat is no longer suitable because it's too hot in the winter. The thermalization cannot happen, and so you have to do something else. So yes, that could be more soybean supply from areas not currently in soybeans at all, and this, our estimate, is not accounting for that.
Okay.
So it's not a total effect, but it's less of a partial effect than the Schlenker and Roberts effect, because the Schlenker and Roberts effect assumes both constant areas and ignores the changes in cropping intensity. Going one step further, we're not fully yet at the whole land allocation model, because then you need a Costino type analysis. I address that convincingly.
Okay, thank you. Thierry Brunel, you have a question?
Yes, thank you very much, Pierre, for your very interesting presentation. So if I understood you well, you account for the effect of climate change on the propensity of farmers to adopt double cropping.
Yes.
Right? That's
in current areas. Yeah, in current areas.
Yeah. Okay.
In current soil areas.
But do you account for the effect of climate change on the suitability for double cropping? Is it something that you account? Yes.
Implicitly, yes.
Okay. Okay.
Yeah, because it's observational. So you could view the observation as the accumulation of suitability and economic incentives. If farmers are growing it, it's because it's feasible first, and second, because they have an economic incentives to do it.
Okay. Right. Thank you very much.
Okay. Any other questions from the floor? I have some questions. Maybe I will start with one if we still have time. I was wondering, you were talking about the benefits, adaptative benefits of this double cropping, but I was wondering if you have any idea on costs on the environmental side on this intensification in terms of using of agrochemical inputs or soil nutrient or water loss. Do you have any idea how this double cropping could be harmful and have some other costs that you don't take into account, but if you have any idea?
I haven't thought about it, but I know that you think about these things in your paper. Well, so currently, soybeans, I don't think they use a lot of fertilizer. They might use a tiny bit, but usually there's hardly any synthetic fertilizer used. Not as much as you would on a commercial wheat farm, I think. So if you add I mean, I could speculate that there is some nitrogen fixation going on with the soy, and so that you don't need to put as much synthetic fertilizer on the wheat than you would on a regular wheat. But still, to the extent you're going to put more inputs, there's probably going to be some leaching, and there's going to be some environmental cost. Now, you know, these crops are grown for world markets. So the additional crop you get is maybe going to offset another one at the other end of the planet. And so, yeah, so you have local pollution, but you have pollution elsewhere as well. I mean, it could be at the other end of the planet, or it could be in a neighboring county. It's hard to I mean, yes, we could do a local analysis, but is that really relevant in itself? It's, yeah, it's relevant for people who manage these particular areas that we're focusing on, but we don't know what the effect on other area is and what the net effect is, if we can compute such a thing as a net effect given. I mean, I'm talking about local pollution, but it's not really local. I mean, if you're talking about leaching, it all goes in the Gulf of Mexico. So the contribution would be more here, but there could be other lesser contributions elsewhere, I guess.
Okay, thank you, Pierre. I think that's
I add one question or not?
A very short one and very quick answer.
Okay. Thanks, Raja. When you put when you do your double cropping model, your fractional logit, why don't you introduce time fixed effects? Because I didn't get if your measure was
because it's a cross section. It's not a panel. It's a cross section.
You sum over 2030 to 2000. You sum the share. No, I didn't get it. But so why don't you do like? Why do you sum over such a long period and don't take a year?
Farmers don't know what the weather is going to be next year. So the idea is that they're making the decision based on the climate, not based on the weather. When they have to decide whether to plant wheat or not in the fall, they don't know what the weather next year is going to be. They don't know if they're going to have time to harvest the second crop. So they're taking a bet based on their central climate. Either they think they're in an area that is suitable, or that on average they're going to be able to make the second crop, or they don't. But using a panel is I think is assuming too much of farmers. So the idea is that what determines the overall propensity to grow is climate. And then of course there are fluctuations. So we see that in the data. One year you will have double crop in a cell, and then you will have less the other year. So there are some fluctuations, maybe driven by price changes or events that happen in the fall. So if there's like rainfall and you can't get your machinery in the field to plant the wheat, then even if you wanted to plant it, you can't, right? So there is variation from one year to the next. But what determines the propensity, we think, is the climate and not the weather. The overall propensity, right? Which is what matters for long run outcome. You know, it's not if whether one grid cell is going to plant one year or the next. What matters is like the overall propensity to grow on average winter wheat with soy. So it's in our head, it's a cross-section question, not a panel question. But I know other papers have used panel data, and we actually criticize that in our paper.
Thank you.
Explain why we didn't publish it.
Thank you, Pierre.